In section 2.2, I'd already mentioned the word histogram, and that's what we're going to be looking at now in section 2.3. A histogram is a tool that we use, or a graphical representation of the data, to make it easier to see the shape of the data, the shape of the distribution. In a histogram, we have a graph consisting of bars of equal width drawn adjacent to each other unless there's gaps in the data. The only reason the bars would not touch in a histogram is if you had zeros for a frequency count there. So on a histogram, the bars touch. This would be different from a bar graph where the bars don't touch. On a histogram, you're talking about quantitative data. If the bars don't touch, we have a bar graph. So if the bars touch, we're discussing a histogram, and you can tell just by looking at the graph that represents quantitative data. If you see a graph where the bars don't touch, you can tell just by looking at the graph that that's categorical data. The horizontal scale represents the classes for the quantitative data values. The vertical scale represents the frequency or the count. The heights of the bars will correspond to the frequency, and the histogram is basically a graph of the frequency distribution. For example, here's the IQ scores for children that had low levels of lead exposure. And so you see here along the bottom, these numbers right here correspond to the gaps between the classes. Remember, we said that this is going to start at 49.5. There's your 49.5 right here. In between 69 and 70 is 69.5. So this bar right here, this first bar, represents this frequency. This bar right here, the height, represents this frequency. Do you see? And so forth and so on. Because of technology, our graphing calculators can graph these things for us fairly easily. The histogram to the right represents the weights and pounds of member of a certain high school programming team. How many team members are included in the histogram? Notice we have gaps here as well. These are the heights. In order to answer this question, how many team members are included in the histogram, all you got to do, remember, is look at the count. How many people are included in this first class? 2, and the second one, 1, and the third one, 0, and the fourth one, and the next one, and the next one, and then 2. So to figure out the total number of the team members, we just add these numbers together. 2 and 1 is 3, and 4 is 7, and 2 is 9, and 2 is 11. So it looks like there would be 11 total team members. We see gaps in this distribution. What might account for the gaps in the distribution? What do these numbers here represent? They represent weights in pounds of members of a programming team. Male, female. Typically guys weigh more than girls, right? That might account for it. This went beyond the scope of the question, but you had raised the question earlier about, well, are we supposed to figure out what they mean? Well, if it seems reasonable, you can go ahead and observe that. But that seems reasonable to me. A relative frequency histogram. Notice the shape of this histogram right here has the exact same shape as this histogram right here. The reason the shapes of the histogram are the same is because they represent exactly the same information. But instead of looking at count on your vertical scale, we're looking at percents. But the shape has to be the same because we're talking about the same population here in our distribution. The population is still people's IQ scores that in this research problem that had low lead exposure. The shape has to be the same if the population doesn't change. All right, here's another question. It says the histogram to the right represents the weights in pounds of members of a certain high school programming team. What is the class width? Very similar to the question we just did. What is the class width here? Remember how to determine the class width? It's 20. What are the approximate lower and upper class limits of the first class? The lower class limit for this first class, the first class is this bar right here. The lower class limit would be approximately 100. The upper class limit would be not 120, but 119. The next class would then go to 120 to what? 139. Do you see why we couldn't use 120 and say that this first class here went from 100 to 120 and then 120 to 140. You can't do that. This is wrong. Why is this wrong? It overlaps. And if you had a weight of 120 pounds, where would they go? In the first class or the second class? You see the problem? So you can't do that. Since the numbers are 100, 120, 140, 160, I'm okay with letting this lower class limit be 100, but then the upper class limit has to back off by 1. So that your class width is going to be 20. Remember, to get the class width, we look at the difference between consecutive lower class limits or the difference between consecutive upper class limits. 120 minus 100 is 20. 139 minus 119 is also 20. So our class width of 20 is good. It actually goes to 239 for the upper class limit there. So let's go ahead and finish writing these out. So we're going to go 140 to 159, 160 to 179, 180 to 199, 200 to 219, 220 to 239, and that's it. Notice we have 1, 2, 3, 4, 5, 6, 7 class widths. There's 1, 2, 3, 4, 5, 6, 7 bars that represent those 7 class widths. It's just that it looks like it goes out to 240 because that's the 239 is really close to 240. But these are the actual class widths right here. Oh, if there is 240, then I would go, okay. Oh, I understand your question now. Your question, I think, and tell me if I'm wrong, I think your question is, what if somebody weighs 240 pounds, where do they go? We would need another class. Whenever you're creating a histogram, you have to look at your maximum value and your minimum value and make sure they fit within the classes you designate. Let's say we had a 350-pound student. Then I would have to have this bar extend out, and I would just have one person down here by themselves. But I would have to have all those numbers in between to show that I have that gap there. And then I had a person that was actually 300 and whatever pounds. And then I would just have blanks right here because there would be nobody that weighed that much. And that makes it easier to spot that this person in this situation would be an outlier. An outlier is a data value that is very much unlike the other data value. An outlier can skew the data so that it pulls it to the left or to the right. There is a gap. This part right here would be the gap, but this person right there would be an outlier because they are different. Interpreting histograms. The objective is not simply to be able to construct a histogram, but rather to understand something about the data. When graphed, a normal distribution has a bell shape, and the characteristics of the bell shape are the frequencies increase to a maximum and then decrease, and then there's symmetry from left to right. So here is the graph of a bell curve or a normal curve that is superimposed over our frequency histogram, our histogram for the IQ scores. What is the shape of this distribution of the red bars? Well, it closely follows, not exactly, but it closely follows that of a normal distribution. So it's similar to a normal distribution. And remember, we said normal distributions are symmetric and bell-shaped. That you want to write down. You need to, in your mind, associate the word normal with symmetric and bell-shaped. Definitely write that down. Normal means symmetric and bell-shaped. The center of this data appears to be somewhere about right here. So that would be close to maybe 90, just looking at the scale here. How much variation is in the data? The variation is the wiggle room. How much wiggle room is there? We're going to look at some formulas. We're going to let the calculator tell us the standard deviation. And then we ask ourselves, are there any outliers? Looking at this graph, does there appear to be any outliers? No, it looks like the distributions are pretty consistent here. Now, I mentioned the word skewness. A distribution of data is skewed if it's not symmetric. So it's going to look lopsided. Another word for skewed might be lopsided. It extends to one side more than to the other. We say data is skewed right or positively skewed if it has a longer tail to the right. The data is skewed left if it has a longer tail to the left. So if your data looks like this, would this be skewed left or skewed right? And would this be skewed left or skewed right? Well, let me write something down that's corny, but it'll help you remember it. The tail tells the tail. Whatever direction the tail is, by the tail I mean the thin, skinny part of the distribution, that's going to be the direction that your data are skewed. So here, the tail end of the data kind of goes off to the right. This distribution would be skewed right. Here, the tail of the data trails off to the left, so this would be skewed left. And if your data are not symmetric, then they are skewed one way or the other. And I would be interested to know if you could tell me if they're skewed left or skewed right. The table below shows the frequency distribution for the rainfall on 52 consecutive Thursdays in a certain city. Use the frequency distribution to construct a histogram. Do the data appear to have a distribution that is approximately normal? So looking at this distribution, here's our class. We start out at 0 and we have a maximum of 1.39. So looking at our data, we have 25, a count of 25 close to 0. So we know automatically this graph is not going to be the one that represents our data because we got to start out high. Then we go to 12. It's going to drop down, but it's still fairly high, isn't it? So we go from 25 to 12 to 4 to 2, then we jump up to 7, and then we have a 1 and a 1. Look at these two distributions. Out of A and C, which one do you think it might be and why? You think it might be A? I tend to agree with you. But why do you think it's A? Look at the frequency right here. This frequency is 25. On C, that goes up to 30. This one goes up to 25. Do you see the difference there? That's how you would go about determining which one of those graphs actually represented the frequency distribution. Look at the count. Do you see how these numbers right here correspond to the numbers along the bottom here? And the numbers on the count right here correspond to these numbers right here? That's one of the things you're going to have to learn how to do, is look and see how those things correlate. So let's talk about the shapes of some distributions. What shape does this one look like? It's symmetrical, definitely. Bell-shaped. And what did I say symmetric and bell-shaped meant? Normal. This is a normal distribution because it is symmetric and bell-shaped. Let's look at this distribution. There's just not a whole lot of variability there, is there? We call this distribution uniform. If you're playing on a sports team, you wear a uniform, right? Uniform so that you all look the same. Well, on a distribution that's uniform, all the data values look to be about the same. The frequency looks to be about the same. It's symmetric, but it's also uniform, meaning it's leveled out. It's not perfect. See, there's a gap right here between the third to the end. There's a gap right there. It's a little bit lower. It's a little bit higher here. But that's okay. It's still uniform. In the world of statistics, we're not talking perfection. We're talking close enough. And that's a judgment call, and that sometimes gets hard in the beginning. But it's close enough. This distribution, notice I'm just kind of tracing along the tops here. How does that look to your eye? Skewed how? The tail end is this region down here. This is the tail. Do you see that? The bulk of the data, it looks like it's kind of been shoved over here to the left. And that's why you probably want to say skewed left. I always got that backwards whenever I first started looking at these distributions. Because, hey, the bulk of the data is to the left, so why isn't it called skewed left? Well, it's not called skewed left because the tail tails the tail. The direction the tail is going is the direction of the distribution, the skewedness. Here's the distribution here. You see how I'm just kind of tracing along the tops of these bars? And when I trace the distribution out with a yellow highlighter, it makes it a little easier, I think, to tell the direction of the skew. And this one is skewed left. You will be asked to identify a distribution by its shape. Is it normal, uniform, skewed left, skewed right, bimodal? Bimodal would be a distribution, it's not on here, But let me show you one that would look like bimodal. If we had a distribution that looked like this, there's no symmetry there. But you see how there's two peaks? This would be an example of a bimodal distribution because we have two separate peaks. And I don't know that this author really focuses on that, but I've seen it in other books and it didn't hurt to tell you. All right, here's an example problem. Would you expect the distributions of these variables to be uniform, unimodal, meaning one mode, or bimodal, symmetric or skewed, and then explain why? So here's the situation. The ages of people at a Little League game. Who all goes to Little League games? Kids and parents. Predominantly. There may be a few grandparents there, older siblings, whatever. But wouldn't you expect the distribution to be, if this is starting out at age 0 and this is age 100, the distribution you would expect to look something like this, where you have a lot of kids and then maybe a lot of parents 10, 15, 20 years older, but we would expect to see a shape that looks like that, wouldn't we? What shape is that? Bimodal. Part B says the number of siblings of people in your class. Well, in order to figure out the shape, draw a picture. Our frequency goes on the left. Here's no siblings. You're an only child. You have one sibling if you have either a brother or a sister and nothing else. You have two siblings if there's 3 kids in the family. 3, 4. How many of you in here have no siblings? You are an only child. Show of hands. How many of you have only one sibling? There's 2 kids in the family. So we picked up a few more, so it's looking like this. Maybe picked up a few more. How many of y'all have 3 kids in the family? How many of y'all have 4 kids in the family? Wow. We got big families here. How many of y'all have 5 kids in the family? There's a couple of you. 6 kids, big families. 7 kids, 8, 9. Okay, fine. We're trailing off here. But what's happening with this distribution is we would expect in America the average family has 2 point whatever kids. I'd hate to be that point whatever. But we expect to have some kids that are only kids, a few more, and then max out around the 2, and then it's going to drift off because here's the Duggars out here. Meet the Duggars, right? That 17 kids, 20 kids, whatever, and counting. They're out there, but they're way out there. So what shape would this have? Do you think it would be symmetric, skewed? Skewed how? We expect more people to come from smaller families. Pulse rates of college-age males. If we're drawing a shape for this, most biological functions, birth weights of babies, pulse rates of a uniform population, don't do males and females, don't do fit and unfit because that changes things. But the average college-age male's pulse rate, whatever it is, most of them are all going to center around a point. And then we're going to have a few that are lower and a few that are higher. Really unfit, really fit, and so forth. Anything that's physical, a physical attribute like that's got a numerical value to it, typically these are normally distributed. The world is normal. We're normally distributed. So this would be symmetric and bell-shaped, or we would call that normal. And then the last one here is the number of times each face of a die shows up in 100 tosses. So we got our frequency, and then how many faces are on a die? 6. Now we're assuming it's a fair die, which means that each side is equally likely to turn up, right? What shape do you expect this to have? Uniform. If each face has, if you've tossed the die 600 times, we expect to get about 100 1s, 100 2s, 100 3s, 100 4s. So this would be a uniform distribution. So just through talking it out, it's easier, I think, to see these shapes here if you draw a picture. The instructions here didn't tell us to draw a picture. The instructions said, what type of distribution would you expect? Well, I have a hard time reading a scenario and then just blurting out an answer. I need to see the picture, which is why we use a lot of graphics and statistics. You've heard him say picture's worth 1,000 words, right? The picture makes it easier to interpret or to see the distribution. So we draw pictures. They're not perfect. It's just a general idea. And then the last thing we're going to talk about today is assessing normality with a normal quantile plot. A normal quantile plot is sometimes called a QQ plot. depending on what software you're using. And it's how we assess whether or not a data distribution is normally distributed. Normal becomes very important when we start running some statistical analysis later on this semester. We need to know that our data come from a normal distribution. So what we would do is we would do a normal quantile plot, and that's plotting our data values here against the z-scores. These are the data values. These are the z-scores. Have we talked at all about a z-score yet? A z-score follows the formula. Z is equal to your data value, whatever it happens to be, minus the mean divided by the standard deviation. And we went over population parameters and sample statistics, right? Does this z-score represent a parameter or a statistic? Oh, well, now's a good time to review. Parameter versus statistic. For the mean, the population parameter is the Greek letter mu. For the statistic, the center of our data would be this x bar. Remember, when you see a bar over a variable, you're talking about an average. So this is our data value minus the average data value in the z-score. The standard deviation, the parameter, somebody said it looked like a sideways 9 or a sideways p or something. But whatever, that's the parameter. This would be the sample statistic. The parameter for a percent would be a Greek letter P, a standard P. The statistic would be a P with a hat over it. We want to have a normal distribution. In a normal distribution, the points that when you plot the x values against their z-scores, you would have a fairly straight line. So notice here we have a fairly straight line here for our data. It's hovering around this green line. All right, so our points here kind of hover around this line. They don't look to be taking on any special shape. However, if you look at these points and you remember your parent functions from college algebra or high school or whatever, that graph of the points looks kind of like a square root function. Do y'all remember square root functions? Okay, algebra wasn't really much of a prereq for this course, so I'm going to remind you. If we had to graph y equals the square root of x, it would look like this, as opposed to the data points being scattered rather evenly around here. There's also another graph that this second one represents when we plot our x values against the z-scores. This graph, these data points right here, look to be taking on this shape. Do y'all remember what graph this shape has? This was y equals the square root of x. This is y equals x cubed. Do y'all remember that? In order for your data to be considered normal, these points need to take on this linear value, not a particular shape when they're plotted, like the square root function. Another function that you'll see quite often with your data, if it's not normally distributed, you'll see a shape that looks like this maybe. Even though when we do a linear regression, which you don't know how to do yet, don't worry about it. I haven't told you how to come up with these graphs. I can do that later. What I'm telling you is, in order for data to be considered normal, your points have to be kind of randomly scattered without this pattern to them about a straight line. Not even this particular straight line, just a straight line. These green lines here represent a regression line, a line of best fit. If you see a pattern here, like either the square root or a cubic function, then your data are not normally distributed. That's what you need to know. That's what you need to take away. So if I were to give you a normal quantile plot, could you look at it and tell me if the data are normally distributed? Hopefully, yes. You will have homework questions that provide you an opportunity to look at normal quantile plots and tell me, are these data normally distributed or not? If they're not, you need to be able to recognize why. You don't have to recognize that it's a square root function or a cubic function. I'm not going to make you recall those parent functions from college algebra, but you need to be able to look at it and tell me what about this graph makes this not normal. Here we've got all of our data bunched up at once, and then it kind of shoots off to the right. While this line may be the line of best fit, these data are clearly not in a linear pattern. While this line here may be the line of best fit, I do see some symmetry right here where these points are curving below the line and these points have almost the same curve above the line, and that reminds me of this cubic function right here. But this looks random enough that it looks like these points are not following any set pattern. They are from a normal distribution.